Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to YouTube channel Chandan Physics. In this video, we are going to discuss refractive index and wave impedance of electromagnetic waves. Let's begin. Definition of refractive index. For a medium, the refractive index is defined as the ratio of velocity of light in free space and the velocity of the radiation, or we can say electromagnetic waves in that particular medium. That is, refractive index n is equal to the ratio of velocity of light in free space c divided by velocity of the radiation or electromagnetic waves in that of medium, let v be the velocity. Means we compare the velocity of that electromagnetic wave in that of medium to that of velocity of electromagnetic waves in free space. Now we can easily calculate what be the refractive index for electromagnetic waves when it travel in vacuum and when it travels in n medium. The refractive index of electromagnetic waves when it travels in vacuum is given by is equal to C divided by V. Here velocity of electromagnetic waves in that of vacuum, which is given as one by mu naught epsilon naught under root, that is the velocity of that electromagnetic waves in this medium. That one is equal to C, as we say 1 by mu naught epsilon naught under root. When we put the values of mu naught and epsilon naught, then we obtain that value is equal to the value of speed of light c. We have already derived c divided by c, which one is equal to 1. So, the refractive index of electromagnetic waves when it travel in vacuum, that refractive index is equal to 1. Then we calculate the refractive index of such electromagnetic waves when it travels in case of any medium. Next, the refractive index of EM waves when it travels in any medium is given by n is equal to c by v, or n is equal to c divided by velocity in that of electromagnetic waves of any medium 1 divided by mu epsilon under root. Epsilon is the permittivity of any medium, mu the permeability of any medium. We can write that the permittivity of any medium or permeability of any medium as relative permeability into permeability of free space. Again, in case of epsilon, that is relative permittivity into permittivity of free space under root, or n is equal to c divided by, now separating it as in two terms, 1 divided by mu r epsilon r under root into 1 divided by mu naught epsilon naught under root. 1 divided by mu naught epsilon naught under root, which is nothing but the velocity of speed of light. See, 1 divided by mu r epsilon r under root into c, that c cancelled out. Refractive index of electromagnetic wave in any medium now is equal to mu r epsilon r under root. So, here we show by taking the definition of refractive index, we calculate the refractive index of electromagnetic waves when it travel in vacuum, that one is equal to 1, and again the refractive index of such electromagnetic waves when it travel in any medium, that one is under root of mu r epsilon r, where mu r that is the relative permeability, epsilon r relative permittivity. Next, wave impedance. What is wave impedance? The definition of wave impedance is the ratio of magnitude of E vector and magnitude of S vector is called the wave impedance, and it is denoted by capital letter Z. That is, Z is equal to magnitude of E vector to that of magnitude of H vector ratio. This is the basic definition of wave impedance. As we know, E vector is equal to E naught vector e to the power I k dot r minus omega t, that is the solution of E vector, equation number I, and H vector as H naught vector e to the power I k dot r minus omega t, that equation number 2. Therefore, E by H vector is equal to E naught vector by H naught vector. So the magnitude E by H vector magnitude is equal to E naught vector by H naught vector magnitude, that is equal to Z. So E by H magnitude is equal to Z, E naught H naught magnitude. Another definition of that wave impedance. Now we have to calculate what be the value of for that of wave impedance of electromagnetic waves when it travel in vacuum and when it travels in any medium. Therefore, from as equation number I, that is at equation number let double I, from I and double I we get Z is equal to E vector H vector magnitude, which is equal to E naught vector A naught vector magnitude. To calculate the wave impedance for electromagnetic waves when it travel in any medium. Okay. From Maxwell's equations, from Maxwell's equation, grad cross E is equal to minus del B by del T. As we know, B vector is equal to mu S vector. Therefore, we can use it grad cross E is equal to minus mu del S by del T. As we have already known, the grad operator is equal to I into k vector. That is why we can use it I k vector plus E vector into minus mu del by del T. Instead of S vector, we write H naught vector e to the power I k dot r minus omega t equal to I k vector plus E vector is equal to minus mu, its differentiation as H naught vector e to the power I k dot r minus omega t into minus I omega t. Here we obtain minus minus plus I omega t mu H naught into that much as H vector I k cross E vector. I cancelled out. We have k vector cross E vector is equal to omega as with differentiation with respect to t, that is omega minus I omega. Okay. So mu omega H vector. Taking magnitudes, that we have K cross E vector magnitude as mu omega H vector magnitude, cross product of two vectors, that is magnitude of K vectors, magnitude of E vectors, and sine of angle in between K vector and E vector, that one is 90 degree, is equal to mu omega magnitude of H vector. Therefore, we have to calculate what will be the ratio of E vector magnitude to that of H vector magnitude. So, E vector divided by H vector magnitude as sin 90 is equal to 1. So, we obtain mu omega divided by K. As we know, omega is equal to Kc, or we can say K is equal to omega divided by velocity. K is equal to omega divided by velocity. Therefore, E vector H vector magnitude is equal to mu omega in place of K, that is omega by V. Here omega cancelled out. Therefore, E vector by H vector magnitude is equal to mu V, that is equal to Z. Let I prefer it as equation number, here it is equation number 3, that one as equation number 4. So, we write it as from equation number 3 and equation number 4, from equation number 3 and equation number 4, we get the wave impedance Z is equal to E vector H vector magnitude, which is equal to E naught vector divided by H naught vector magnitude, that is equal to mu V. Okay, anybody can write it as mu in place of V, that is the velocity of electromagnetic waves in any medium, that is written as 1 divided by under root of mu into epsilon. Therefore, 1 mu under root cancelled out. So, it will be mu divided by epsilon under root. It can also be written as in place of mu, that is relative permeability into permeability of free space, divided by in place of epsilon relative permittivity into permittivity of free space under root. Now, separating the terms as mu naught divided by epsilon naught under root into mu r divided by epsilon r under root, that term is called as Z naught, which one is the impedance of free space, into mu r epsilon r under root, that is the expression for Z. Whereas Z naught is the impedance of free space. In this way, we show the expressions for wave impedance for electromagnetic waves. First we define what is wave impedance, next another form in terms of this, comparing these two equations we write it, for V we substitute, and finally we show the impedance for a free space which is equal to mu naught divided by epsilon naught under root. Z naught is equal to mu naught divided by epsilon naught under root. Here the wave impedance that is E vector by H vector magnitude is a real quantity, and the field vector E vector and H vector, E vector and H vector are in same phase. And its unity of Z, as we write it as E, unity of E, volt per meter divided by unity of H, that is ampere per meter. Meter cancel out, that is volt per ampere, which is equal to ohm resistance. So unit of Z is equal to ohm. Okay. So here with the help of this video lecture we understand the concept of refractive index and wave impedance of electromagnetic waves. First we define what is refractive index, then refractive index of electromagnetic waves when it travels in vacuum, and the refractive index of electromagnetic waves when it travels in any medium. Next, wave impedance. First we define what is wave impedance, then various forms of wave impedance. This is the relation of wave impedance, impedance of free space. It is a real quantity. These two vectors are in same phase, and unit of wave impedance is ohm. So, with this useful and informative notes, let me wind up the session. Thank you.